In this video, we'll take a look at what are known as the scales of measurement. Okay, first of all, measurement can be defined as the process of applying numbers to objects according to a set of rules. Now, at first, this definition may look a bit daunting, but let's go ahead and break it down, and I think you'll see that it's really not that bad. So, when we measure something, we apply numbers, or we give numbers to something, and this something is just generically an object or objects. So we're assigning numbers to some thing or things, and when we do that, we follow some sort of rules. Okay, so for example, we all are actually very familiar with measurement. If we measure someone's height, we might have them stand against a wall, and then we take a tape measure and we extend it vertically until it meets the top of their head. And we read off on that ruler how many feet and how many inches they are. So we might read out 5 feet 9 inches, and that indicates their height. So we applied numbers to an object, in this case a person, according to a set of rules. And the rules is you extend the tape measure from the ground vertically up until it reaches the top of their head, where we're level there at the top of the head, and we read off how tall they are. So that's measurement. Now, in terms of introductory statistics textbooks, there are 4 scales of measurement: nominal, ordinal, interval, and ratio. We'll take a look at each of these in turn and take a look at some examples as well, as the examples really help to differentiate between these 4 scales. First, we'll take a look at nominal. Now, in a nominal scale of measurement, we assign numbers to objects where the different numbers indicate different objects. The numbers have no real meaning other than differentiating between objects. So as an example, a very common variable in statistical analyses is gender, where in this example, all males get a 1 and all females get a 2. Now, the reason why this is nominal is because we could have just as easily assigned females a 1 and males a 2. Or we could have assigned females 500 and males 650. It doesn't matter what number we come up with, as long as all males get the same number, 1 in this example, and all females get the same number, 2. It doesn't mean that because females have a higher number that they're better than males, or males are worse than females, or vice versa, or anything like that. All it does is it differentiates between our 2 groups. And that's a classic nominal example. Another one is baseball uniform numbers. Now, the number that a player has on their uniform in baseball, it provides no insight into the player's position or anything like that. It just simply differentiates between players. So if someone has the number 23 on their back and someone has the number 25, it doesn't mean that the person who has 25 is better, has a higher average, hits more home runs, or anything like that. It just means they're not the same player as number 23. So in this example, it's nominal once again because the number just simply differentiates between objects. Now, just as a side note, in all sports it's not the same. Like in football, for example, different sequences of numbers typically go towards different positions. Like linebackers will have numbers that are different than quarterbacks and so forth. But that's not the case in baseball. So in baseball, whatever the number is, it provides typically no insight into what position they play. Okay, next we have ordinal. And for ordinal, we assign numbers to objects just like nominal, but here the numbers also have meaningful order. So for example, the place someone finishes in a race, first, second, third, and so on. If we know the place that they finished, we know how they did relative to others. So for example, the first place person did better than second, second did better than third, and so on, of course, right? That's obvious. But that number that they're assigned, 1, 2, or 3, indicates how they finished in a race, so it indicates order. And the same thing with the place finished in an election, first, second, third, fourth. We know exactly how they did in relation to the others. The person who finished in third place did better than someone who finished in fifth, let's say, if there are that many people. First did better than third, and so on. So the number for ordinal, once again, indicates placement or order. So we can rank people with ordinal data. Okay, next we have interval. In interval, numbers have order, just like ordinal. So you can see here how these scales of measurement build on one another. But in addition to ordinal, interval also has equal intervals between adjacent categories. And I'll show you what I mean here with an example. So if we take temperature in degrees Fahrenheit, the difference between 78 degrees and 79 degrees, or that 1 degree difference, is the same as the difference between 45 degrees and 46 degrees. 1 degree difference once again. So anywhere along that scale, up and down the Fahrenheit scale, that 1 degree difference means the same thing all up and down that scale. Okay, so if we take 8 degrees versus 9 degrees, the difference there is 1 degree once again. That's a classic interval scale right there, where those differences are meaningful. And we'll contrast this with ordinal in just a few moments. But finally, before we do, let's take a look at ratio.